right, this last part is a big warning that in all of our previous examples, we could only substitute when a constant was missing. Remember, that's where we were dividing off values. And so there will be times you cannot use substitution. For example, I can look at this inside, and when I take the derivative, I get 4x cubed, but that's x squared. You cannot do anything with variables and exponents, okay? So in this case, in this class, we don't have any other options. We just would not be able to work a problem like this. So in order to use substitution, it helps if the integrand contains the derivative of the inside. So in other words, that's what I'm looking for, is my leftover. Does that look like the derivative of the inside? And then within a constant, which would be fine. So looking here, get my pen going, I can see that you know, the inside, I'm thinking maybe using x cubed. Why? Because look at chair, that's the derivative. And so that's the key, is you're looking ahead. When I take the derivative, will it be, besides a constant, the leftover piece? Well, this one's perfect. It is the leftover piece. So as I said before, why not just change the order so you can see this directly, that this becomes cosine of u and this becomes du. So it worked out perfectly. The antiderivative of cosine is sine, and then I can simply plug back in my value of u. Now, if you recall, this is the derivative of this. So why not check it? Take the derivative, and the derivative of sine x cubed would be cosine x cubed times the derivative of x cubed. And don't you get this back again? Yeah, hey, there you go. All right, so let's look at another one. On this one here, if I want to get my pen again, if I want to say, why not let my u equal cosine of theta? The derivative of u, remember, is minus sine. Well, that's okay. That's kind of like saying a -1. So I could divide both sides by -1. And this gives me exactly my leftover piece. So this becomes e to the u times minus du. I probably just put the negative out front. The antiderivative of e to the u is e to the u, and then I plug back in what u equals, and I get my answer. Let's think there's one more. So in this case, I can see that it looks like what's in the denominator could be my inside. Notice this one, I'm actually going to do a definite integral where I'm going to find the area. So I'm going to say let u equal t plus 9. The derivative of t is just 1 dt, right? So I don't even have to, well, I can put the 1 because I see it there in the formula. And so again, if I rewrite this, this is really 1 over the square root of t plus 9 dt, where this piece right here is going to become du. And then of course that becomes u. So I get 0 to 16, 1 over the square root of u du. Let's move that square root to the top. So remember that this is the same thing as u to the 1/2, but when I bring it up to the top, it becomes -1/2. And I take the antiderivative, so -1/2 plus 1, -1/2 plus 1. And this gives me u to the 1/2 over 1/2. I flip the 2, and I'm going to go ahead and write the u as a square root. And then finally, don't forget to plug back in u. And now I'm to the point where I can evaluate. All right, so I do my f of b, which is the 16, minus my f of a, which is the 0. So this becomes 2 square roots of 25 minus 2 square roots of 9. which would be 2 times 5 minus 2 times 3, which would be 16 for your final answer. So I know I'm going through these fast, but of course being a video you can sit and pause them, but the key is figure out what u is. When you take the derivative, does that give you what's left over? If it doesn't, then you pick the wrong thing for u. All right, so keep practicing these and you'll get them.